Hello, welcome to lecture 18 of the course. In this lecture, we are going to learn how to create electromagnetic radiation or light quantum mechanically. That is, we are going to study the quantization of light. And we are going to discuss quantization of both propagating electromagnetic wave as well as standing electromagnetic wave. So let's begin. So far in the course, we considered matter quantum mechanically, where we assume that the atoms and molecules have discrete energy levels and the electromagnetic radiation which interacts with the atom or the molecules are classical. For example, in the case of a two-level system, we have this discrete energy level, the ground state denoted by K0 and the excited state denoted by K1, and electromagnetic radiation where the electric field is E. E is created classically and it is written in this form where say eta is the polarization of the electric field, E0 is the amplitude of the electric field, say it is propagating along z direction, then we write it in this form e to the power I kz minus omega t. So here the atom is treated quantum mechanically and the electromagnetic radiation or light as is treated classically. In this lecture, we want to create electromagnetic radiation or light quantum mechanically. That means we are now going to do the quantization of electromagnetic radiation or light. However, before we go further and we do that, let us recall how we quantize something classical. To do that, let us be reminded about the so-called classical harmonic oscillator where a mass is attached to a spring of say spring constant say k and a mass m is attached to it where k also we can write it as m into omega square where omega is the angular frequency of oscillation of the mass. And then you know that the Hamiltonian for this spring mass system is written in this form: h is equal to p square by 2m. P is the momentum, m is the mass, half m omega square q square. Q is the displacement of the mass from its equilibrium position. So here the variables q and p denote position and momentum, and they are canonically conjugate variables because they satisfy the so-called Hamilton's canonical equation of motion. So Hamilton's canonical equation of motions are q dot is equal to, you know that from classical mechanics, q dot is equal to del h del p, and p dot is equal to minus del h del q. Alright, and moreover equivalently they satisfy the so-called Poisson bracket equation qp that is equal to 1. Now to go to the quantum regime, we need to replace these canonically conjugate variables q and p by their corresponding operators. Q is going to replaced by the operator form q cap and p is going to be replaced by the operator form p cap, and this Poisson bracket qp is equal to 1 is going to be replaced by the commutation relation between these operators q and p by this commutator qp is equal to I h bar, and then it is straightforward to quantize this harmonic oscillator. You just have to write the Hamiltonian in the operator form, p in the operator form p square by 2m plus half m omega square q square where q is also again in the operator form. So this is the general procedure for quantization and is known as the canonical quantization method. So this is the method that we are going to adopt even for quantizing an electromagnetic radiation. Basically what we are going to do first is to find the classical Hamiltonian of an electromagnetic field and then look for the associated canonically conjugate variables. Let us consider a traveling or propagating electromagnetic wave in free space described by this electric field E is equal to eta E0 of t
e to the power I k dot r plus complex conjugate, where eta is the polarization direction of the electric field. This is the polarization direction, and E0 of t is the complex amplitude of the electric field. This is the complex electric field amplitude of the electric field, and it characterizes the state of the electric field in a given mode. And also you know that this polarization direction is perpendicular to the wave vector. Now, as I said that this electric field amplitude is a complex quantity, so it has a real part as well as an imaginary part, and we'll see later on that these two quantities, real part and the imaginary part of the complex electric field, is basically going to behave like a two dynamical canonically conjugate variable. Why dynamic? Because as you can see that these variables, real part of the electric field amplitude and the imaginary part of the electric field amplitude is time dependent. That's why it's dynamically variable, and they would turn out to be canonically conjugate. However, before I go on to show you that, let us consider the so-called Maxwell equations in free space, which I am sure all of you must be familiar with. The Maxwell equation in free space are divergence of E is equal to 0, divergence of B is equal to 0, curl of E is equal to minus del B del T, and curl of B is equal to 1 by c square del E del T, where c is the speed of electromagnetic radiation in free space. Now, because of the fact that we are considering a plane electromagnetic wave propagating with the wave vector k, so we can replace delta by ik, right? And if we do that, our calculations become very simple. Then divergence of E, we can write it as ik dot E, curl of E we can write as ik cross E, and curl of B, this equation curl of B is equal to minus curl of B is equal to 1 by c square del E del T, we can write it as del, we can write as ik cross B is equal to 1 by c square del E del T. You know, in the electric field the time dependent part is only there in the complex amplitude, so therefore I can write on the right hand side of this equation, this I can write eta dE0 of t dt e to the power I k dot r, and then complex conjugate part is also there. So if I now take the cross product, so we are basically build up our analysis based on this equation. So what we are going to do now, we are going to take the cross product on both sides of this equation with k. So let me show you how to do that. If I multiply both sides by k, taking the cross product with k, so I have on the left hand side I have this, okay, and on the right hand side I am going to take this I to the other side, then I have here 1 by I c square k cross eta, and I have dE0 dt e to the power I k dot r plus complex conjugate. Okay, so we can use this identity which all of you surely know, that A cross B cross C is equal to A dot CB minus A dot BC. If I utilize this identity, then I am going to apply this here in this equation. If I apply this, then I am going to get K dot B K, right, minus K square B, that is on the left hand side, and on the right hand side I have 1 by I C square K cross eta dE0 of dt e to the power I K dot R. And because of the fact that divergence of B is equal to 0, which means Ik dot B is equal to 0, so therefore this particular quantity is going to be 0, and utilizing this we have an expression for the magnetic field. B is equal to I, this minus sign I am taking to the other side, then I will go up in the numerator, then I by K square C square K cross eta dE0 dt e to the power I K dot R. So what you see, that magnetic field also I am able to express in terms of the complex amplitude E0. This is the reason I said that E0, the complex amplitude of the electric field, characterizes the electromagnetic wave in this case. Now again, curl of E is equal to minus del B del T. Alright, so from here again, if I do the mathematics, I can write it as I K cross E is equal to B expression I already have. So if I take del B del T, then I will get I by omega square. Omega is equal to Kc. Okay, so that's why K square C square is equal to omega square, and I have here K cross E, K cross eta, and I am taking the time derivative, so I have d2 E0 dt2 e to the power I K dot R. Now if I put the expression for the electric field, I have I K cross E is equal to eta E0 e to the power I K dot R, and here I have minus I by omega square K cross eta d2 E0 dt2 e to the power I K dot R. And from here, if I compare both sides, I am going to get d2E 0 dt2 is equal to minus omega square E0. I hope you can see this, because you have K cross E here, eta here, K cross eta here, e to the power I K dot R here, e to the power I K dot here. It get cancelled out, this I and this I also get cancelled, and then you will be left out with this particular equation. And the solution of this equation, as you know, it is simply E0t is equal to E0 or at time 0 e to the power plus minus I omega t. What it means? This means that we are now having two solutions. One refers to the fact that the wave is propagating along the plus k direction, and in that case the solution would be E0 of t is equal to E0 at time 0 e to the power minus I omega t. This is the solution referring to the wave propagating along the plus k direction. And there is another solution where the wave propagates in the minus k direction, and in that case the solution is E0 of t is equal to E0 of 0 e to the power plus I omega t. Okay, these are the two solutions. However, what we are going to do, we are going to keep only one solution, that means just one mode, and we will consider the wave which is propagating in the plus k direction only. And in that case, I can write down the electric field expression E of RT is equal to, this is the mode we are going to consider. Eta is the polarization direction, E0 of 0 now I am putting, and e to the power I k dot r minus omega t plus complex conjugate. So this is the mode of the electromagnetic wave we are now going to consider, and we can then write the magnetic field as well. So that is going to be B of RT is equal to k cross eta by omega E0 of 0 e to the power I k dot r minus omega t plus complex conjugate. So this is the expression for the magnetic field. So therefore we have both the electric field component and the magnetic field component of the electromagnetic wave, and here this E0 complex amplitude of the electric field in this particular mode is obeying this particular first order differential equation, that is dE0 dt is equal to minus I omega E0 of t. Okay, so let me now take E0 of t, which is the complex amplitude of the electric field, as I into A is a constant, and alpha of t, which is a dimensionless normal variable. And if I take E0 in this form, and from this equation I get d of, I will get an equation for this dimensionless variable alpha. So I am going to have d alpha of dt is equal to minus I omega alpha of t. Okay, and this equation, as you can see, fully describe the electromagnetic field in the given mode, because ultimately alpha is related to the complex amplitude of the electric field and A is a constant. So alpha of t overall describe the whole dynamics of the electromagnetic field in the given mode. Now let us express this quantity alpha of t in terms of its real and imaginary part as follows. So we'll write alpha of t, which is a complex quantity. It has a real part and an imaginary part. So let's say, and it's a dimensionless quantity by the way. So let me write, say it is equal to q plus ip, and alpha star of t is equal to q minus ip. However, here I am going to multiply it by a factor given as 1 by square root of 2 h bar, and here also I am going to multiply it by a factor 1 by 2 h bar, where h bar is the reduced Planck's constant. By the way, it has nothing to do with quantum mechanics. This particular multiplication factor is there so that later on you will see the calculations become much more simplified. So that's the reason we are multiplying it by this particular factor, and using these two equations I can express this quantity q and p as well in terms of alpha and alpha star. So q would be, you can do it yourself, you will get that q is equal to square root of h bar by 2 alpha plus alpha star, and p is equal to h bar by 2 square root alpha minus alpha star. Alright, and after having all this, now let us write down the Hamiltonian of the electromagnetic field. You know that the energy of the electromagnetic field is given by, you can just look at any electromagnetics or electrodynamics book. So this is the energy, or which is our Hamiltonian for the electromagnetic wave, is given by this expression. So you have E square, in free space we are actually writing it, so E square plus C square B square. So this is the Hamiltonian. Here the first term and the second term are equal in magnitude, because we are considering the electromagnetic wave in free space. So this first term and the second term, they are equal. So therefore we can write the Hamiltonian H is equal to epsilon 0 d3r e square. Now we have to work out this Hamiltonian. To get an expression for this Hamiltonian, let us consider a volume element, and to do that let me consider a cube where each side is having length L. So this is the cube, let me consider. So this is my x direction, this is my y direction, this is my z direction, and each side is having length L. So the volume would be equal to L cube, right? If I consider this volume, then it can be shown that H is equal to twice epsilon 0 E0 of t mod square into volume. So I urge you to show this, get this expression. You can use the boundary condition for the electric field. Maybe we'll do that in the problem solving session later on. So you can work out the Hamiltonian and you are going to get this expression. So after getting this expression, because you know that E0 of t you have written it in this form, I a into alpha of t. So this Hamiltonian you can write as H is equal to twice epsilon 0 a square into the volume and mod of alpha t square. Now let us take this choice. Let us take this constant a. Let me take it as h cross omega divided by twice epsilon 0 v under root. If I take a as this, where h cross omega is the characteristic energy in the problem, so here h cross omega refers to it has a dimension of energy. It is the characteristic energy in the problem. So if I choose my a like that, then you are going to get H is equal to H cross omega mod of alpha t square. And alpha of t, by the way, you remember that sometime back we have taken alpha of t as 1 by 2h per square root. We have taken it as q plus ip. So therefore this implies h is equal to, if I take the mod of alpha t square, I am going to get omega by 2 q square plus p square. So what these Hamiltonian expressions will remind you about the so-called simple harmonic oscillator Hamiltonian. Here q and p are canonically conjugate variable. However, let us confirm that q and p are canonically conjugate variable in our given problem. To do that, we need to check if the Hamilton's canonical equation of motions are satisfied. You know the Hamilton's canonical equation of motions are q dot is equal to del h del p and p dot is equal to minus del h del q. And from this equation, we have del h del p is equal to omega p, and p dot is equal to minus omega q. And from these two equations I can have q dot plus I p dot is equal to omega p minus I omega q, which I can write as minus I omega q plus ip. And this expression on the left hand side I can write it as d of dt q plus ip. Okay, and apart from this multiplicative factor of 1 by 2 h bar if is there, then you can easily see that this quantity is nothing but alpha of t. So d alpha of t dt is equal to minus I omega alpha of t. This particular equation earlier we obtained using Maxwell equations. Now we have obtained it from the Hamilton's canonical equation of motion. So thereby it confirms that the q and p are indeed canonically conjugate variables. Now, having identified the canonically conjugate variables quantization is pretty straightforward. You simply need to you replace q by the operator q cap and p by operator p cap, and you have to also invoke this commutation relation qp is equal to I h bar, and this, in that case, you can write the quantum mechanical Hamiltonian for this mode of the electromagnetic field. It would be omega by 2 q square plus p square. Okay, again you can also replace this classical quantity alpha of t, which is a complex quantity, by an operator a, which is the so-called annihilation operator. You can write it as 1 by 2 h bar q plus ip, and alpha star of t you can replace it by an operator a dagger, that is equal to 1 by 2 h bar q minus ip. And if you do that, you can immediately check that you are going to get a dagger is equal to 1. Okay, and from here you can write down the Hamiltonian in terms of this variable a, in this operator a and a dagger, in this form h cross omega a dagger a plus half. So which is exactly the same Hamiltonian you must be familiar with in the context of harmonic oscillator, quantum harmonic oscillator. So what you see, that an electromagnetic wave consists is basically the mode, electromagnetic mode behaves like a harmonic oscillator. Each mode of an electromagnetic wave behaves like a harmonic oscillator. In fact, an electromagnetic wave consists of infinite number of modes, and each mode behaves like an independent harmonic oscillator, and the total Hamiltonian, quantum Hamiltonian for an electromagnetic wave can be expressed as a sum of all the modes, contribution from all the modes. So you have h cross omega lambda, you are taking sum over all lambda. Lambda represents the lambda-th mode, so you have a lambda dagger a lambda plus half, and energy E is equal to sum over E lambda, and that is equal to sum over h cross omega lambda n lambda plus half, where n lambda is the number of, this is the number of photons in the lambda-th mode. Moreover, the classical electric field and magnetic field are also now operator in the quantum realm. So electric field, which we have earlier written as, in the classical case we had it like this: eta E0 of t e to the power I k dot r plus complex conjugate. Recall that E0 of t we have taken it to be ia alpha of t. So therefore in the quantum regime, the electric field is now going to be represented by the operator, and we have this eta a already, this constant we have already know what is that, that is h cross omega divided by twice epsilon 0 v under root, and alpha is replaced by this annihilation operator a of t. You have e to the power I k dot r, and because this is quantum mechanics, so complex conjugate would be replaced by Hermitian conjugate, or I can write it as E is equal to I h cross omega twice epsilon 0 v under root eta a e to the power I k dot r minus a dagger e to the power minus I k dot r. So this is the complete expression for the electric field operator in the quantum regime. Similarly, we can write down the expression for the magnetic field. Classically, we had this magnetic field expression in this form: B of RT is equal to K cross eta divided by omega E0 of t e to the power I k dot r plus complex conjugate. So from here it is easy to write down the expression for the magnetic field operator in this form. The way I have done it for the electric field operator, you can do it for the magnetic field operator as well. Please do it yourself and so that you can write the magnetic field operator by this expression k cross eta A, which is an annihilation operator, which is time dependent. Time dependence is included in the operator A, e to the power I k dot r minus A dagger e to the power minus I k dot r. Okay, so this is the expression for the magnetic field operator. Let me summarize what we have learned so far. We considered a propagating electromagnetic wave having complex amplitude E0t. E0t has a real part and an imaginary part, and we write E0t complex amplitude of the electric field in terms of a constant A and a dimensionless variable alpha of t. Alpha of t is a complex quantity and it has this real part q and imaginary part p. We write it in terms of q plus ip apart from multiplying it with a appropriate factor, and which as you have seen later on simplify the calculations. Then we have worked out the Hamiltonian for the electromagnetic field, and Hamiltonian turns out to be this expression which I have asked you to work it out. If you try it better, otherwise I'm going to do that in the problem solving session. Here this V is the quantization volume, and in terms of this alpha of t parameter, ultimately we write the Hamiltonian in terms of q and p, and as you can see this Hamiltonian is expression we are getting is quadratic in q and quadratic in p, which is exactly of the similar form of a harmonic oscillator. And we also established the fact that q and p are canonically conjugate variable, and therefore we can apply the quantization procedure, and therefore we can take q as the operator q cap, p as the operator p cap in the quantum regime, and the Hamiltonian we write in terms of the operator in this particular form. And again we introduce two dimensionless operator A and A dagger. A is defined like this, which is the so-called annihilation operator. A dagger is the usual creation operator. In terms of annihilation and creation operator, the Hamiltonian finally we can write it in the very familiar the harmonic oscillator Hamiltonian that we often encounter. After doing that, we can immediately write the expression for the electric field in the quantum regime. It will now be an operator E cap, and then the corresponding magnetic field also can be written for the propagating wave. So that's how we have done the quantization. Now we have considered only one mode of the propagating wave, and we find that each mode of the electromagnetic field behaves like a harmonic oscillator. So this is the key result of the whole analysis, and the quanta of this wave is known as photons, which you must be knowing. And for traveling wave, the photon has a definite momentum p is equal to h cross k, and it has a definite energy E is equal to h cross or h bar omega. So that's how we define the photon of a traveling or the propagating wave. Now the question is, what about electromagnetic wave confined to a cavity? What about their quantization? Because you know that light confined in a cavity forms a standing wave. So let me take you through the quantization procedure of a standing electromagnetic wave. However, to do that, first let me begin by writing the Maxwell equations. So to do the quantization of standing electromagnetic wave, let me write down the Maxwell equations first, and these are the Maxwell equations. Divergence of E is equal to 0, divergence of B is equal to 0, curl of E is equal to minus del B del T, curl of B is equal to 1 by C square del E del T. Now you know that because of the fact that divergence of B is equal to 0, I can write this magnetic field in terms of curl of A, where A is the so-called vector potential. Now in terms of this vector potential, I can write this expression curl of A is equal to minus del B del T in this particular form, and thereby I can write curl of E plus del A del T is equal to 0, and because curl of E plus del A del T is equal to 0, I can write this quantity E plus del A del T as a gradient of a scalar potential or a scalar quantity minus grade of phi, and then electric field I can express in terms of scalar potential phi and the vector potential A in this form, and the magnetic field we can write in terms of the vector potential A. Now from divergence of E is equal to 0, if I put the expression for the electric field, then I get this equation. If I now take divergence of A is equal to 0, which is known as the Coulomb gauge, and also if I choose phi is equal to 0, that means the scalar potential, which is basically the electrostatic potential, if I take it to be 0, which means that there is no electrostatic potential in the background, then I can simply write the electric field in terms of vector potential, and the magnetic field is anyway, we can write it in the form of a vector potential in terms of vector potential as curl of A. Now having this electric field and magnetic field in this form, let me consider a standing wave, which is standing electromagnetic wave, that is formed due to the presence of two plane mirrors separated by a distance L. Now we can write down the equation for the vector potential like this: A of zt is equal to eta is the polarization direction of the vector potential, A of t is the amplitude of the vector potential, and then we have sine kz. And similarly the electric field, we write it as its polarization is eta, and E of t is the amplitude of the electric field, and sine kz is the spatial part of the electric field. And then magnetic field can be written because of the curl of A in this particular form. Now you have to apply the boundary condition. Please note that I am here rushing through the things, but this procedure, if you follow, it's not difficult at all. So now boundary condition we have to apply. Here it is easy to see because these are plane mirrors. At the mirror end, electric field must vanish. So therefore electric field at z is equal to 0 and electric field at z is equal to L should vanish. And from this particular equation, E of Lt is equal to 0, we must have sine kl is equal to 0, which is sine kl is equal to 0. I can write it sine n pi, n is an integer. From here I have kn is equal to integral multiple of pi by L, n is an integer. And because of this boundary condition, as you can see that the wave vector is now discretized because of the boundary conditions. Then what we do next is, using these Maxwell equations, we can easily obtain a wave equation in terms of this vector potential. I urge you to just get this equation, very straightforward. You can get it applying the Coulomb gauge that we have taken. Now because of the fact that electric field is equal to minus del A del T, and this vector potential has the spatial dependencies only along the z direction, so therefore I can write delta to A delta z2, that is delta to A. This one I can write in this form, and del A del T E is equal to minus del A del T. So this expression I can write in terms of the electric field 1 by c square del E del T. This is what the form I write. And from here the time derivative of the electric field is equal to c square. I take it to this other side, then I have this expression. And because A is a function of z, and as you can see, because I have taken A to be of this form, this vector potential, so if I differentiate is twice with respect to z, then I get this one. I will get a k square factor, and therefore I will have c square k square A, and which is I write as omega square A, because omega is equal to kc. So time derivative of the electric field is equal to omega square A. And after that we define a quantity, dimensionless quantity alpha of t as this. It's a mathematical trick that I am now applying, omega A minus I et. and n is a constant which we can choose later on. Then alpha dot t, you can easily follow this mathematics here. We can show that alpha dot t satisfy this particular equation, that d alpha of dt is equal to minus I omega alpha t. So similar kind of treatment we did in the case of the propagating wave as well. So alpha of t, as you can see, it describe the dynamics of the standing electromagnetic wave or the light field completely, as we have seen similar thing in the case of the propagating wave as well. Now next we find out the Hamiltonian of the electromagnetic field, and to here while we do the calculations to find out, work out this Hamiltonian for the electromagnetic field, we consider the quantization volume to be of this form, where L into L perpendicular square. Here L means the length of the cavity along the mode axis. So you see this is the mode axis along the z direction. So this is the mode axis, and perpendicular to this one is transverse direction is along this one, and another one is perpendicular to the page. And suppose we imagine a quantization volume like that. L perpendicular is the size of the quantization volume along the transverse direction with respect to this mode axis, and if I take that, then I can write the work out the Hamiltonian for the electromagnetic field in this particular form. I will request you to do this yourself. Otherwise, anyway, we are going to do that in the problem solving session once again. And now, choosing the constant n in this form, s cross omega by epsilon 0 v, we can write the Hamiltonian finally in this form. And this is the same form of Hamiltonian we encountered in the case of the propagating wave treatment as well. But here is a difference. The difference is choosing the constants. You see, in the case of the propagating wave, the constant was a, and the constant we have chosen to be like this. This is the constant we have chosen, and here we have chosen the constant in this form. Now there is a difference is only in the factor of 2 differences there. There is a physics reason why it is so, because of the fact that in the case of the propagating wave, the energy of the wave is distributed throughout the volume, throughout the uniformly it is getting distributed throughout. But in the case of the standing wave, the energy is preferentially located close to the nodes of the cavity mode instead of it is being uniformly distributed. And this is the reason this factor of 2 is coming here. And also it gives a meaning to the photon in the case of the standing wave as well. In the case of a standing wave, a photon occupies the average, on the average, only half the geometrical volume of the cavity. So I hope you get the idea. Now rest of the procedure is again simple. Then as usual we define this variable alpha of t in terms of q and p, as we have done in the case of the propagating wave, and then finally we can write the Hamiltonian h in this form, omega by 2 q square plus p square. And again we can establish that q and p are canonically conjugate variable, which I leave it to you to do that. And following the exact quantization procedure, similar procedure as that we have adopted earlier, we can now quantize the Hamiltonian. We can write down the Hamiltonian in this particular form. Then defining the annihilation and the creation operator A and A dagger, we can finally write down the Hamiltonian, quantum mechanical Hamiltonian for the standing electromagnetic wave. And what you have seen is that even in the case of a standing electromagnetic wave, the mode behaves like a harmonic oscillator when quantized. And the quantum mechanical operator form of the electric and magnetic fields for standing electromagnetic wave can be expressed in this form. Here we are writing the expression for the operator for the electric field, the vector potential, and the magnetic field. And you can also check the difference between the electric field expression for the magnetic field, electric field, and vector potential with that of the propagating wave. And you can very easily work these expressions out. So I'm leaving it to you to do that. Otherwise, we may again do that in the problem solving session. However, now let me make few comments about the concept of photon in the context of a standing wave. As you know, that even in the case of standing wave, the quanta of light is called photon, but there is a subtle difference between the standing wave photon and the photon in the propagating wave, because in the standing wave, as you can see, it is formed due to the superposition of two counter propagating wave, and these waves has wave vector in the opposite direction. For example, this blue one has this the solid line. It has a wave vector say plus k, and this one has say wave vector minus k. So because of that reason, if you find out the average momentum of a photon in the standing wave, it is going to be 0. So average, let me write here, this is very important, and it distinguishes the photon from that of the propagating wave. Average momentum of a photon in a standing wave is equal to 0. What does that mean? This means that if you make a measurement of the momentum of the photon, measurement of momentum of a photon in the standing wave, you will either get plus h cross k or you will get minus h cross k. This is what it means. However, the photon energy is going to have a definite value in the standing wave. The photon energy is going to have a definite value, and it is h cross omega.
Let me stop here for today. In this lecture, we have seen that if electromagnetic radiation is created quantum mechanically, that is if the electromagnetic radiation is quantized, then each mode of the electromagnetic wave behaves like a independent harmonic oscillator. In the upcoming lectures, we are going to study the quantized nature of light. See you in the next class. Thank you so much.